Okay, so today's video is about projectile motion. We're going to go through all the different kind of variations, questions that you might see, and all the tools that we can use to solve them. But the real learning is done through practice, so I'll attach a sheet and you should try that with the video. So watch the video, take notes, and then practice. That's important. Projectile motion is one of those first kind of topics in A-level that might be a bit confusing for some people. Before you can do any projectile motion question, you need to know a bit about SUVAT and you need to know a bit about vectors. But we'll go through that as well briefly in this lesson. So let's take an example. So find the horizontal distance x reached by the projectile. So we shoot in a projectile up at an angle theta with initial speed u, and it travels some horizontal distance x before landing on the ground. So it starts here and ends there. Now the first thing you need to do with any projectile motion question is to split it into horizontal and vertical components. Horizontally, there is no acceleration, so it's just distance equals speed times time. S equals ut, and it's very simple. We just have three quantities that we need to worry about. And vertically, we have acceleration, right? G is pointing down always at 9.8 meters per second, so we need to use SUVAT. Now, depending on your exam board, you might have only these three listed, or maybe these four, or if you're very unlucky, only these two. But these are the two kind of core equations of SUVAT, and the rest are derivations. You can actually try and derive these next three by just putting in substitutions. For instance, v equals u plus at, so you put that in there, and after some substitutions you'll end up with that one over there. Okay, so how do we break it up into vertical and horizontal components? Well, we draw vector triangles. Theta is the angle of our initial speed. And if we want the horizontal component of that theta, then we need to take the cosine, right? Because this is the adjacent of this triangle. And if we want the vertical component, we need to take the sine, because it's the opposite of this triangle. Now, we start off by splitting it up and listing all the values. And we try and fill in all the values that we know, and then later we'll see which ones we want to figure out. So what do we know? First, we know the horizontal component is u times cos theta, just by the vector decomposition. So that'll be u cos theta here. And the vertical component of the initial speed u is sine theta. So that'll be u sine theta here. Okay. Now, another thing that's almost always true is that the acceleration will be minus 9.81 meters per second squared. Now, why do I put a minus here? Because projectile motion uses vectors, right? We're using displacement, we're using velocity, initial, final, we're using acceleration. Those are all vectors, so direction matters. And when we're dealing with vectors, we always need to choose a kind of positive and a negative direction. So I will just choose this side as positive for the horizontal, and I'll choose up as positive for the vertical. And because I chose up as positive, that's why I've given here a u sine theta, because the vertical component is pushing upwards. And positive to the right is why I've given u cos theta here a positive value. And then you can see that acceleration, because it's always pushing down, is going to be negative. Now, you can choose different positives and negatives, but if you just choose one and stick with it, then be consistent with it, you won't go wrong. So I just choose this. Okay, what else do we know? Well, let's look at the question. Find the horizontal distance x reached by the projectile. So here's where we look at our starting and ending point. We start here and we end over there. And then we have this x. Now x is a horizontal quantity. So really, it's our horizontal displacement. So we fill in x here of our horizontal displacement at the end. That's what we will want to find later on. Now, do we know anything else about the vertical? Well, we don't know the final velocity, and it says nothing about the time. But the displacement, actually, we do know, because it's gone all the way up here, and then it's come back down to the same vertical height, the starting height. So the vertical displacement is 0. All right? Okay, last thing that you need to know is that, well, these quantities here are independent of each other. So they can be anything you want. But between the vertical and horizontal, time is shared. So time will be exactly the same. And if you look at the horizontal, we have the initial speed, the initial velocity, and we have x. So we need time to actually find the last unknown. So let's put a question mark for time as the quantity that we want to know. And then we'll put it here as well, because this is the quantity that we want to know. This is the missing link that will solve the equation for us. Let's put a better question mark. Okay. Also notice that SUVAT always has 4 quantities in any equation. So if you have 4 quantities, or rather if you have 3 quantities, you can find the next 2. But if we want to be efficient, we want to find the time, right? Because then if we have the time, we can find x using this equation. So if we want to find that time, we need to start with the vertical, because here we have enough known quantities to find the time. So we have s, we have u, we have a, and t that we can deal with. Let's choose an equation from our list that has only those 4 quantities. And it's this one. This is also one of the most common ones that you'll use most of the time. So yeah, expect to see that one again and again. Now we just fill in the values that we know. So s equals 0. Let's just write it. S equals ut plus 1/2 at squared. Initially s is 0. 0 equals, this is u sine theta times t plus 1/2 at squared, 1/2 of minus 9.8, so minus 4.9 roundabout t squared. Okay, so maybe using this unknown theta and u is a bit confusing at this stage. So let's give some numbers. Let's put a 5 meters per second for u, and let's just put 30 degrees here. In doing so, we can just fill in these ones. So this will be 5 cos 30, and this one will be 5 sine 30. Okay, so then let's fill it in over here. 0 equals 5 sine 30, which is 2.5, if you put that into a calculator, minus 4.9 t squared. Okay, we have one equation, one unknown, and we can find the time, which is great, because later we can use that time to find x. So we factorize t 2.5 minus 4.9 t, like so. and we get two solutions. T equals 0 and T equals, now I need a calculator, 0.51. Now notice we have two solutions for T, so which one is it? Well, SUVAT is a mathematical equation, and it will just give you all the solutions where our conditions are true. So S being 0 is a condition which is met at the beginning and the end. So T equals 0 is this solution, and T equals 0.51 is that solution. So of course, the time taken that we're going to use in our horizontal equation is going to be T equals 0.51. Now, the horizontal is always an easy thing. It's just distance equals speed times time. So if we want x, we'll just write x, distance equals speed, 5 cos 30, times time, 0.51. And if we put that in a calculator, we will get 2.21 meters. There we go. We found x equals 2.21 meters. And we can pretty much apply this exact logic to any projectile motion question. So let's write that in a list. So I've skipped the writing of the list, but basically we start by listing the horizontal and vertical quantities and equations. So this list that I made here, right, for this side and that side. And then we choose our start and end point, which can be from here to here, or, it could be from here to there, whatever the question asks. And then we fill in the values that we know, but remember that it's vectors. So sometimes you might have negative quantities for displacement or whatever it might be. Then remember, time is shared between the two, so these will always be the same. Everything else is independent. And then we choose one of the equations to get us closer to our unknown. And more often than not, you'll see that it is this equation that we're using that we're solving for time. Now, I will attach a bunch of practice questions that you can try of this style. But there is more to projectile motion, and I'll show that right now. Okay, so sometimes you will not be given that much information as we did just in the previous question, where we want to find the horizontal position, right? There are some things that we need to know about projectile motion, and remember, that will really help us solve these questions much quicker. And the first thing is that a projectile, ignoring air resistance, draws out a parabola in space. And that means that there are certain symmetries that we can use to help us solve questions. The first of these symmetries is, well, if we take any 2 points in this parabola, cut it off like that, I will choose the ground, then everything is equal and opposite on the other point. So let's say that this is u at this angle, and starting going there, u at that angle. Then at the end over here, the final speed, v, all right, will equal u, the initial speed. That means to say that if we shoot it off at 5 meters per second this way, then when it lands on the ground, it will hit with a 5 meter per second again. This is ignoring air resistance, but this is a symmetry that you can use. Of course, the angle will also be the same. And you can choose any 2 points that you want. And you can also choose any component that you want. Say the vertical component here is 1 meter per second at a height of 0.5 meters. Then if we go to the other side, where it's a height of 0.5 meters, it will be going down by 1 meter per second, the vertical component. That is the symmetry of a projectile motion. And you can use this to solve harder questions. Another thing that we need to know is some of the special points. Now, I'll write in yellow the horizontal. Horizontal is simple because horizontal is always the same regardless of where we are. Let's say we are now going at 2 meters per second to the left at this point. Well, it will always be 2 meters per second to the left because we don't consider air resistance. It will be 2 meters per second to the left the whole time. What about vertical? Well, for vertical, there are some special points. First of all, we need to know the top. The top is when the vertical is equal to 0. All right? This is V vertical. And the bottom is where the verticals will have its maximum quantity. So here we'll have V vertical is at a max, and V vertical upwards, this case, will be also a max. All right? U vertical equals max. But really, in practice, the things that you need to remember, I will list them down. So to summarize those, the first thing we need to know is symmetry. Whatever comes up will go down at the same speed if we're looking at equal heights, right? One up, one down. The horizontal will always be the same speed no matter where we are, and that also means that it will be at the top the same speed. And at the top, the vertical component goes to 0, and we can often use that to calculate the maximum height and among other things. So let's try a practice question that uses one of these things. Here, question: find the maximum height reached by a projectile launched 30 degrees above the horizontal at 5 meters per second. Well, this is pretty much the same question, but in this case we want to find how high it reached, so this h over here. So let's do the same thing. First we go to the horizontal and we list the things that we know, and then we write a vertical equation where we will have to consider SUVAT, so acceleration time final velocity. Now we choose our 2 points. In this case our 2 points will be again the beginning, but this time the end. And now let's fill in the values that we know. Horizontal component, we're using cos of 30 degrees, 5 meters per second. So that'll be 5 cos 30. And the final kind of displacement, well, we don't really know what that is. Actually, we do. Again, it's a parabola. So we know it's x over 2, actually. But you'll see that we won't actually need it. And time, well, we don't know what that is. Okay, let's go to the vertical. So for the vertical, we're starting down here, we end up there. So we give it a positive h. Put in a minus 9.8, downwards acceleration. Initial velocity is upwards, so that'll be 5 sine 30. And the final velocity we can actually use here is v equals 0. The vertical component is 0, as we said before. So we want to find h. Well, notice here we don't actually need to use the horizontal component at all, because we already have 4 quantities. If we have 3, we can find the other 2. We just need to find a SUVAT equation which fits these 4 quantities in it. So have a little think. Okay, so the SUVAT equation that we need to use is v squared equals u squared plus 2as. Okay, so we fill in the quantities. Vertical v is 0, u is 5 sine 30 squared, and then we have negative acceleration, so minus 2 times 9.81 times our unknown h. Now we solve for this equation, and we will get that h equals 0.319 meters. So it's not very high, but the angle also wasn't very high. So why did I write the horizontal component anyway? And why did I write this x over 2 here? Well, sometimes you might have to use this x over 2. It's a symmetry that we can use. We could have figured out the time, for instance, in this case, and then we could have gone there and used the time over there, and we could have found x over 2. Or we could have already known x over 2, found the time, popped it back there, and figured out something like that. So it's always good to just write everything you know if it doesn't take you too much time, because then you know what information you have to deal with. Now, there is something else that we also need to know, and I'll show you that right now. And that is turning our vertical and horizontal components back into a vector with an angle. So I'll show you by example. Now, we already knew from symmetry that if we are shooting something up at u, then it will go down at v, which is equal to u, with the same angle. But what if we give it an initial speed, like so, and then we're asked, okay, what angle does it land, and at what speed does it land? Yes, speed. So how do we do that? Well, let's again approach it the same as we do any other SUVAT equation. And let me just put in a value over here. Let's just stick with that 5 meters per second, as usual. So we give it 5 meters per second, and we also need to know the height. So let's say this is 30 meters, some high cliff. We throw a ball 5 meters per second horizontally. And now let's fill in the values. So S U T S U V A T. Okay, what is the horizontal displacement? Well, that is some unknown that we don't know, and maybe we don't really care about, so let's not fill it in. What about u? Well, u is 5 meters per second, and what about t? We don't know. Okay. What about the vertical displacement? Well, it's minus 30. Minus 30 because we're going down. And remember, I'm just choosing up as the positive direction. But we need to be consistent, so I will always choose up as the positive direction. So that means minus 9.8 for the acceleration, as always. What is the initial vertical component of velocity? Yes, it's 0. It's 0 because we're not moving up or down. Now, the other ones we don't really know, but what we need to find this final kind of speed and angle is we need to find the final vertical and horizontal components. So if we can find this horizontal final velocity, and we can find this vertical final velocity, well, then we'll be able to turn it back into a kind of speed and angle. So this is the one that we want to find. And I'll talk about the horizontal in a minute. So looking at this is the one we want to find. We don't really need to switch between horizontal and vertical components. So we can straight away go to use a SUVAT equation. Do you know which one? Yes, that's right. v squared equals u squared plus 2as. Okay, v squared, our unknown, is equal to u squared, initial 0, plus 2as. So it will be 2 times minus 30 times minus 9.81. So v squared is equal to 588.6. And we take the square root, and v is equal to 24.3 meters per second. Now, I should be careful. It's not actually equal to 24.3 meters per second. It's equal to minus 24.3 meters per second. Because look at the diagram. V will be going down. So you can't just blindly trust your SUVAT equations. You need to also keep in mind which direction it's going. So minus 24.3 meters per second because it's going down. What about our final horizontal velocity? Well, this one's very simple. The final horizontal velocity doesn't change. So our final horizontal velocity will just be 5 meters per second. So let's draw that out. Our final speed, which is down some unknown v, will be composed of a final vertical going down of minus 24.3 and a horizontal that's going along at 5. Okay. So how do we find that final speed? Well, it's just a matter of Pythagoras. It's a triangle. So we can just do the square root of the sum of the two. And when you do that, you will get 24.77 meters per second. And that's how fast we're going down here, 24.77 meters per second. Now you might think, right, that's very close. Well, 5 is much less than the amount that we're going down, right? So that would make sense. Now how about the angle? In this question, we're asking to find this angle theta over here. So let's draw that. This angle theta over there would have been kind of this angle here. Now, that angle is the same as this angle inside of the triangle. And if we want to find that angle, we can use, not Pythagoras, we can use trigonometry. Now, in this case, we do have all sides of the triangle, so we could use any of the trigonometric equations that we want. But I would recommend to always use tan, because this is one of the quantities that you've calculated from those two. So if you made a mistake, it's better to just stick with the tan. So tan opposite over adjacent. So theta is equal to inverse tan of 24.3 divided by 5. Tan is opposite over adjacent. And if you do that, you will get 78.4 degrees. Okay, so we found that our final speed is 24.77 meters and it's 78.4 degrees. Now, how would we fully describe this motion? We can always try and describe it in an explicit way, and like that there will never be any confusion. So we'll say like this: final speed of 24.77 meters per second at an angle of 78.4 degrees. And now we need to be explicit about where we're measuring our angle from. I would say something like clockwise below the horizontal. And you can always vary it with how you describe it, but if you choose a direction clockwise, anti-clockwise, above, below the horizontal, or vertical, like that you'll never be ambiguous. This is exactly describing our final speed in a kind of, a speed angle format. And so just in the same way as we went from the speed angle format to the vertical horizontal components, we can go back and find it at the end. And this is an important skill to have. Mainly it's important for the mathematics part of mechanics. You won't be asked this so much in your physics A level. However, it is still good to know about. Now, the last thing that you need to know about projectile motions, and this is usually a 1 marker that's asked at the end of some calculations, is state any assumptions that you've made. And what we've not talked about is that we're basically assuming there's no air resistance. And the reason that we're assuming there's no air resistance is because our horizontal component is not changing, right? It's just a constant velocity. And we don't have any vertical air resistance either. We're just assuming a constant g acceleration down. And another thing that we almost always assume is that it's a point-like particle. So we're treating this as a point, not a ball, which would mean that, perhaps it would actually touch the ground when its center of mass is slightly above the ground, right? So no air resistance and a point-like particle. Now, what happens if we were to include air resistance? Well, we had this nice perfect parabola shape for no air resistance, right? So this would be for no air resistance. But if we include air, all of a sudden, it will start slowing down in the horizontal and vertical directions against its motion. And so it starts curving and becoming steeper like this. And hopefully that makes intuitive sense to you. But yes, don't forget that we are working under an assumption here. So I hope you found the video useful. If you have any questions, just let me know. And until next time.